Okay, so part 2 of product operators, and so far you've looked at how you can use product operators for a single spin, and I hope you've seen that they produce basically the same result as you get from the vector picture, which is encouraging and helpful, but of course if that's all they did, there wouldn't be much point in product operators. But of course the thing we are really interested in is what happens when you have coupled spins, because it's only when you have coupled spins that you can get the really interesting effects in NMR. And the product operator method comes into its own in dealing with coupled spins, which basically the vector picture can't deal with at all. And we're going to start out by considering two coupled spins, which is relatively straightforward. And we'll see that although it gets more complicated, you nevertheless can continue to use a geometrical interpretation. So those diagrams we've been using about how X and Y and Z rotate operators, they still apply, and then we'll have to supplement those with a couple more, but we will still maintain this geometric interpretation. And using this, we'll be able to understand two really crucial concepts in NMR. That's coherence transfer and the generation of multiple quantum coherence. And all modern multiple pulse NMR hinges on these two effects. So it really is very important for us. So first of all, I'm going to describe the operators that you need to describe two spins. Now, when we had one spin, I said that to describe the density operator, you needed Ix, Iy, and Iz, and these represent the X, Y, and Z components of the nuclear spin angular momentum. Now, if we're going to have two spins, then we need three operators which are called I1X, I1Y, and I1Z, and they represent the X, Y, and Z components of the spin angular momentum for spin 1, and that's why they have the subscript 1. We also need to include, for completeness, an operator which I didn't mention before, the unit operator, which I'm going to call E1. In fact, it does absolutely nothing in this theory, but it's helpful to include it at the beginning so you can see exactly how all of the details of the operators pan out. So one spin can be described by these four operators, the unit operator, and then Ix, Iy, and Iz for spin 1. And you won't be surprised to hear that for spin 2, you have an exactly equivalent set of operators, I2X, I2Y, I2Z, and another unit operator, E2. And if you want to discuss two spins using this quantum mechanical approach, it turns out that you need to consider all possible products of a spin 1 operator with a spin 2 operator, and there will be clearly 16 of those. So the description of the state of two spins requires 16 operators. For one spin we actually only needed 3. For two spins we're going to need 16. And of course this is why this theory is called the product operator theory, because when you start dealing with coupled spins you have to deal with products of operators. So let's have a look at what those products are. So first of all, I'm going to take all the products where one of the operators is E1, and I'm going to make its product with the other four operators for spin 2. So if you look at that row, all of the operators include E1, and then the second operator is E2, I2X, I2Y, and I2Z. So that's 4 of these operator products. And now I do the same thing, except now the operator for the first spin is I1X. And then I make the combination. So I get I1X with E2, I1X with I2X, I1X with I2Y, and so on. And here we come across the first little complication we need to worry about. If an operator product contains two X, Y, or Z operators, you have to include a factor of 2 for normalization purposes. So the operator product I1X, I2X has to be written as 2 I1X, I2X, because it's got two X, Y, or Z operators in it. On the other hand, the operator product I1x E2 doesn't need a factor of 2 because it's only got one product in it. And then we just carry on going. Here are all the products involving I1y, I1y E2, I1y E2x, and that has to have a 2, and so on and so on. And you've got the hang of it now. The final lot are all the operator products involving I1z, so I1z E2, and so on and so on. And there are all of the 16 possible product operators. And the density operator at any time will be some linear combination of all of these 16 operators. You'll be glad to hear that it's very unusual to get to a point in a calculation where you've got that many operators. You usually deal with a rather smaller number as you go along. Now the question is, what do these operators mean? Because I was at pains to point out when we were talking about one spin that Ix means magnetization along X, Iy means magnetization along Y, and Iz means magnetization along Z. And the point of the operators is that they have this very simple connection with the things that you can observe, the magnetization. Now this connection is maintained when you come to two spins, but there are simply more possibilities. So don't worry about all the complexity in here. We'll go through this in quite a lot more, but this just summarizes what all of these operators stand for. So for example, I1z, that stands for Z magnetization on spin 1. That's hardly a surprise. And I2z, that stands for Z magnetization on spin 2. So that's again not a surprise. I1x, that corresponds to X magnetization on spin 1. And I1y corresponds to Y magnetization on spin 1. But these are a special kind of magnetization. It's called in-phase X and Y magnetization, and I'll explain in some detail in a minute what that means. And likewise, they're equivalent operators on spin 2. Now things like 2I1x I2z and 2I1y I2z, these are called antiphase magnetization. So I1x I2z is antiphase magnetization on spin 1, and 2I1z I2x, that's antiphase magnetization on spin 2. And again, I will talk about what that means in some detail because it's rather important in all of this theory. And then finally, you've got a series of operator products which have got two X or Y's in them. So things like 2I1x I2z or 2I1x I2y. And these correspond to multiple quantum coherences. We mentioned about multiple quantum transitions before, and they are represented in this theory by these operators. And again, we'll have a lot more to say about that in the third session. And there's one more operator, the 2I1z I2z. That's a special kind of non-equilibrium population, which we'll also come across. So we'll come back across these, but these are the interpretations of all of these operators. Now, if you think about two spins, we're going to have free evolution and we're going to have pulses in our sequences. Now, when we have free evolution, of course, they're going to evolve under the offset in just the way that one spin did. But there's a new thing that's going to come up, and that is the coupling. All right? So the coupling is going to have an effect on these operators, and that's the new feature of the two-spin system. So first of all, I want to consider what the effect of the coupling is on these operator terms. So if you have free precession, that just means allowing the system to evolve just under the influence of the static magnetic field. You have three terms in the Hamiltonian. You have the first term, omega 1 I1z. That represents the offset of spin 1 in exactly the same way that we had before for when we had a single spin. And we have another term, omega 2 I2z, and that represents the offset of spin 2. And then we have a new term, 2 pi j I1z I2z, And that's the term that represents the coupling. And we saw this in the first lecture and when we were talking about energy levels. If you're wondering about the 2 pi, the tradition is that J is always given in hertz, but in my expression there, omega is in radians per second. So I have to multiply the J by 2 pi in order to get all the units consistent. Now, if we're going to consider the evolution under free precession, we have to consider the effect of each of these 3 terms in turn. The offset of spin 1, the offset of spin 2, and then the coupling. Fortunately, these terms commute, as that says in quantum mechanics, which means that you can apply them in any order you like. So you can do the offset and then the coupling and then the offset, or you can do the offset and the coupling. It doesn't make any difference, but you do have to consider each term in sequence. So in terms of the arrow notation, if you start with the density matrix at time 0, the first arrow has got the offset of the first spin, the second arrow has got the offset of the second spin, and the third arrow has got the J coupling. So that's how we're going to do it. Now, the first 2 are easy. They're rotations about Z, and we've already done that. But the third arrow, the one that says 2 pi J I1Z I2Z over it, that's a new term. We haven't come across that yet. And you'll be glad to hear that the answer is already known. And so we just have to supplement our table with a couple of new identities. Now have a look at these. It says e to the minus I theta I1Z I2Z. That's the J coupling term, acting on I1x. And lo and behold, on the right, you get cosine times the operator that I first thought of, the I1x, and a new term multiplied by sine, which is 2I1y I2z. And likewise, if you take the coupling term and act on I1y, you get the old term times the cosine and a sine times the new term, which is 2I1x I2z. And you'll notice what's happening here. Under the influence of coupling, the in-phase term, I1x, is evolving to the anti-phase term, 2I1y I2z. The in-phase term, I1y, is evolving to the anti-phase term, 2I1x I2z. And that is the crucial thing in this theory about what coupling does. It interchanges these 2 in-phase and anti-phase terms. Notice though that the angle appears with a half in there, and that turns out to be important. The angle is not cos theta like we had before, it's cos theta over 2. So to take an example, if I start with I1x and I allow it to evolve for the coupling for a time tau, over the arrow I write h times tau, so that's 2 pi j I1z I2z times tau. And I realize that all I need to do is to use the first identity and put theta is equal to 2 pi j tau. And then that identity applies, and I can work out that I1x goes to I1x and 2I1 I2z in the way shown there. Notice that the angle is cos pi j tau. It's half of this angle theta. So that's how you would describe evolution under coupling. And you can see that if you set the time tau to 1 over 2j, you would get the cosine term would go to 0 and the sine term would go to 1. So if you allowed the coupling to evolve for a time 1 over 2j, you would find that it went from in phase to 100% anti-phase. Now if you've ever looked at any multiple pulse sequences, they're always full of delays that are 1 over 2j. Right? And that's why, because that's the delay that gives you this transfer between in phase and anti-phase. So that's the effect of coupling. Now we just need to tidy this up by thinking about the problem the other way round. So if I start with an anti-phase term, like 2I1X, I2Z, and I allow that to evolve under the coupling, what happens to that? Well, these are the identities you'll need, and you'll see there that the antiphase term goes to the in-phase term. So under coupling, you just have this exchange between the antiphase and the in-phase terms. Notice it's the half angle again. So to take an example, if I start with 2I1Y, I2Z, and I allow that to evolve, I can use the second identity, and I get cos times 2I1Y, I2Z, and sine times I1X. And as ever, it's half the angle. And again, if you have the delay set to 1 over 2j, you'll get complete conversion from the antiphase to the in-phase. And that idea will come up very often. Now, what that means is that the effect of these coupling terms can be represented using one of these diagrams. So before we were using these to look at how X, Y, and Z rotate things. Now these two diagrams show us how the coupling affects the term. So if you look at the one on the top left, if you start, actually we won't do that, sorry, we'll start with the one on the top left and the term YZ. And the diagram says that YZ goes to minus X. And that means if you start with the operator 2I1Y, I2Z, it goes to the new operator I1X, all right, with a minus sign in front of it. So these terms, these diagrams you can use to explain to determine the effect of the evolution of coupling. So you can just start at anywhere in these diagrams and it'll tell you how the coupling evolves. It works just as well for spin 2. So if your antiphase term is on spin 2 rather than spin 1, then all you need to do is swap the indices 1 and 2. So for example, if you take the evolution of 2I1X, I2Z, and you can get that from the right-hand part of B, that tells you it goes towards Y, and that's what's written out in the first line. You get sine theta over 2 times I1Y. If you want to do the evolution of 2I1Z, I2X, they're just swapped over the 1 and 2, then it goes to I2Y. Right, so these little diagrams apply equally well both ways round. So that's how we're going to deal with the coupling. But what I now need to do is to explain what I actually mean by this business of antiphase and in-phase, because that's really rather crucial in all of this. And so the best way to think about this is if we start with a term like I1X, which I call in-phase magnetization on spin 1. If we then just allow that to evolve freely and observe the free induction signal, what you discover you get is two lines, one at omega minus pi j and one at omega 1 plus pi j. And if these two lines have the same sign. And of course these are the two lines of the spin 1 doublet. Right? That all looks a bit strange because it's written in radians per second, but if you wrote it in hertz, it would be at the frequency plus or minus j over 2. So this is why we say I1X is an in-phase magnetization, because if you allow it to evolve, it gives you the doublet where the two peaks have the same sign. And it's in phase on spin 1 because the doublet comes out on spin 1. Of course, you can phase the spectrum how you like, but I've just written it here so that the real part comes out with absorption mode. And if you have I1Y, that is in phase magnetization on spin 1. But because it's along the y-axis, it'll just come out with the opposite line shape. So instead of the real part being two absorption modes, the imaginary part will be two absorption modes. So there's just a 90-degree phase shift between those two. So I1X I1y is an in-phase magnetization, meaning that if you observed it, you'd see a doublet with both lines of the same sign. Now, you won't be surprised to discover that if you take an anti-phase term, like 2I1x I2z, and you allow that to evolve freely, what you get is, again, a doublet on spin 1, but this time the two lines are of opposite phase. One is down and one is up, and that's why it's called antiphased. So the two lines of the spin 1 doublet, but this time they are antiphase. And again, if you look at the corresponding term 2I1y I2z, then it's the same thing. The two lines are in antiphase, but it'll be 90 degrees shifted in phase. So these terms are called antiphase because when you observe them, the two lines of the doublet have the opposite sign. So this little diagram is just summarizing all of this. In black at the top, you've got the two doublets that you would normally see in the spectrum of two coupled spins. And I1x gives you an in-phase doublet on spin 1, and I've phased it so that x comes out to be absorption. So that's what you see there. And 2I1x I2z, that gives you antiphase on spin 1, and I've phased it there again so it comes out in absorption. I1y is in phase, but of course here it comes out as being dispersion because it's along the y-axis, and likewise for I1y, I2z. If I just redo all of that and phase y to be absorption, now you can see that I1y is in phase, and is in the absorption mode, as is 2I1y, I2z. But it's absolutely up to you which way round you decide to have absorption or dispersion. So these are the spin 1 terms. Then you have an exactly equivalent set of terms on spin 2. So I2x is in phase on spin 2, and 2I1z I2x is antiphase on spin 2. And that's what I show there. And likewise, if you rephase it, so y is absorption, you've got in phase I2y and antiphase I1z I2y. And this idea of the antiphase term turns out to be absolutely crucial in all of this, because these antiphase terms turn out to be the ones that do all the interesting stuff. Now, before we can analyze anything in a bit more detail, we just need to review the Hamiltonians we're going to use. If it's free precession, we've already seen what the Hamiltonian there is. It's got a term for the offset of spin 1, a term for the offset of spin 2, and then the coupling term. Now, if you're going to apply a pulse, you're going to apply a pulse if it's a homonuclear system. For example, if you're dealing with two protons, you're going to apply the pulse to both of the spins. So you have a term, omega 1 I1x, that's for the pulse applied to spin 1, and omega 1 I2x, that's for the pulse applied to spin 2. And these two terms also commute, so like the terms in the free precession Hamiltonian, you can apply them in any order you like. If you're going to do a pulse about y, you won't be surprised to find that we just change the thing to I2y. And for example, it may be that you decide that you're going to apply the pulses either just to spin 1 or to spin 2. So here I've described the Hamiltonian for a pulse only applied to spin 2 about the y-axis. So the Hamiltonian is different depending on which spins you're pulsing and what phase the pulses are. When we talk about heteronuclear spin systems, for example, if the two nuclei are proton and carbon of different sort, it's quite common to switch to an IS notation rather than calling the operators I1 and I2, because it just creates a stronger contrast between them. It doesn't alter anything, it's just a notational thing. So the operators are IX, IY, and IZ, and SX, XY, and SZ, rather than I1X, I2Y, I2Z, and so on. And again, the Hamiltonians rewrite, you've got omega I, IZ, omega S, SZ, and so on. And for the pulses, if it's a pulse to the I spin, it's with a term in I, and if it's a pulse to the S spin, it's with a term in the S. Right? And this is just a change of notation. It doesn't alter the underlying process. Okay, so we've put all the bits and pieces together now. We know how to describe pulses and free precession, and we've got some idea about what these in-phase and anti-phase terms mean. And we're going to look at these first of all, and we're going to look at how this plays out with spin echoes. And you're never going to get away from spin echoes in this course. Now you've already looked at the spin echo and you've seen that the offset is refocused. That's a very special property of the spin echo. And what we're now going to imagine, look at, is how the J coupling gets involved in the spin echo, because it's actually different. Now if you have a homonuclear system, for example 2 protons that are coupled, when you apply the 180-degree pulse in the spin echo, both spins experience the pulse, and what we're going to show in a moment is that this refocuses the offset, but the coupling is not refocused. So the offset gets refocused but not the coupling, and that's a fundamental difference between these two things in the spin echo. On the other hand, if you turn to a heteronuclear system, for example a carbon-13 coupled to a proton, you can choose whether or not to apply the 180-degree pulse to the carbon, or to the proton, or to both. And depending on how you do this, you can refocus either or both of the offsets, and you can choose whether or not to refocus the coupling. So in a heteronuclear system, you've got a lot more control over what goes on. And this turns out to be of exceptional importance in multiple pulse experiments on heteronuclear systems. You constantly use spin echoes of different kinds to control whether or not the coupling or the offset or both or neither is being refocused. So I make no apology for spending quite a long time on this, because this is so important as a building block in multiple pulse NMR. So first of all, we're going to look at the homonuclear system. So 2 coupled spins of the same kind, such as 2 protons. So here's my spin echo, and now you notice I've taken away the first pulse. And the reason for that is I want to be able to start with different kinds of magnetization. So the spin echo is just delay 180 delay. And we're going to start, for example, with I1X. That means in-phase magnetization on spin 1. And we're going to see what happens during this delay 180 delay. Now, I assure you that if you work it out, you'll find that the offset is refocused. And if you don't believe me, you can work it out for yourselves. So we're going to leave the offset out of this altogether, and that is refocused. And what we're going to do is focus in on what happens to the coupling. So the first thing we need to do is to allow the coupling to evolve for a time tau. And we look at our little diagram and we realize that I1X goes to 2 I1Y I2Z. And the angle is pi j tau, all right? Because it's half of this 2 pi j tau. So that's the delay tau. And then we have the 180-degree pulse. And we have to remember that the 180-degree pulse is going to be applied to both spins. And I'm assuming the 180-degree pulse is about the x-axis. So what will that do? Well, the I1x term is completely unaffected. The I1y term will go to minus I1y. And the I2z term will go to minus I2z. So the net result of all of that is absolutely nothing, right? Because the two minus signs associated with the I1y and the I2z cancel one another out, and the I1x is unaffected anyway. So in this rather strange case, the pi pulse has no effect whatsoever on the evolution at this point. So that's done the delay and the 180, and now we need to finish it off doing the second delay. So far that's what we've got, and what we now need to do is work out the effect of the coupling during the second delay. And we have to do each term, remember, so we've got to do the term in I1x, and then we've got to do the term in 2I1y, I2z. So let's do the I1x term first of all, and it's the same as the things we were doing before. You have to remember that this cos pi j tau term, shown in red, that's just a harmless factor which you carry forward in the calculation. So what I've actually got there is I1x going to 2I1y, I2z, which is what you can read off our little diagram. The red term is the factor that carries forward, and then the black term, the cos pi j tau and the sin pi j tau, these are the two new terms that have risen because of this evolution. So that's the I1x term, and now we need to do the same with the 2I1y, I2z term, and again the original sin pi j12 tau term, which I've written in green, that just carries forward as a harmless factor, and 2I1y, I2z, if you look at the diagram, evolves to minus I1x. So we've now done the effect of the final delay for the two terms, and so we can gather everything together and see what we've got. And I've just grouped them a little bit. We've actually got two terms in I1x, and we've got two terms in 2I1y, I2z. Now it looks like a bit of a mess, but if you remember your trigonometric identities, you'll remember that cos 2 theta is cos squared minus sine squared, and sine 2 theta is 2 sine theta cos theta. And so that first term is actually cos 2 pi j tau, and the second term is actually sine 2 pi j tau. So we can simplify that to this, and that's the end of the calculation. So we've done tau, 180, tau. And what have we got? The offset is refocused, because I said it was. The J coupling is not refocused. The result you get here depends on tau and it depends on J. So the J coupling is not refocused by this sequence. In fact, the J coupling basically continues to evolve for the entire time to tau. And that distinction in the spin echo between what happens to the offset and what happens to the coupling is extremely important in this theory. So we've shown here that what happens is the coupling evolves throughout and the offset is refocused. Now I just did that starting with I1x, and it may be that that was just a special property of I1x, but it isn't actually. If you go through all sorts of other starting states like I1y or 2I1x, I2z, you can try some of these for yourself. You'll find that you always end up with the fact that the J coupling continues to evolve. And in fact, when you look at this table about what the results you get, you discover a very, very helpful little dodge for doing these calculations. And that is that if you want to calculate the effect of a spin echo, it's equivalent to the coupling evolving for the total time 2 tau, followed by the 180-degree pulse. So when you calculate the effect of a spin echo, you don't have to do delay 180 delay. You can actually get exactly the same result by doing twice the delay and then the 180, and you can do that in a trice. So this is a very good dodge for calculating spin echoes, and I recommend that you use it when you do calculations because it just saves a lot of effort. So let's see an example of that. Suppose I start out with an antiphase term along x, so 2i1x, i2z, and I want to say what happens during a spin echo to that. So the first thing I do is I say, well, the coupling will evolve for a time 2 tau, and notice it's evolving for 2 tau, the total duration of the spin echo, and there's a time 2 tau multiplying the Hamiltonian over the arrow, and so we get cos and sine of 2 pi j tau. And its antiphase along z goes to in phase along y. And then we apply the 180 degree pulse to both spins. And you need to remember that it's about x, so the I1x term is unaffected, the I2z term changes sign, and the I1y term changes sign. So they're all indicated there in red. And so that's the final result. And that's much simpler than doing delay 180 delay. So I'm not saying in the spectrometer you can do this. It doesn't work like that. I'm just saying for the purposes of calculation, you can calculate the effect of a spin echo in this shorthand way. And it works just as well if you start on spin 2 as well. So what I'm going to do now is just show how you might use this to describe the outcome of a very simple experiment, and that's the J-modulated spin echo. So what I'm doing here is I'm doing a 90 degree pulse, and then I'm doing a spin echo, and then I'm going to acquire the signal. Now, of course, the 90 degree pulse, which I've indicated is about y, that will generate x, and we've already worked out what happens to I1x. If you put a spin echo on, you get an in-phase term times I1x, and you get an anti-phase term 2i1y, i2z. And one is cosine modulated, and the other is sine modulated. So what we're then going to do is assume that after the second delay tau, we're going to acquire the signal. And this is what you would typically see. So concentrate on the one on the left to start with. If the delay tau is 0, then this term is 1 and this term is 0. So you just see the in-phase term, and that's what you see there. And then as you increase the delay, you start to get more and more of the antiphase term. And in fact, when the delay tau is 1 over 4j, you get 100% antiphase. And you can see that most clearly on the right, because the antiphase comes along the y-axis. So if I phase y to absorption, you can see that when tau is 1 over 4j, you get 100% conversion to the antiphase. And then if you carry on, the in-phase comes back until you get to when the delay is 1 over 2j, and then the doublet is changed sign. So you get this interconversion of in-phase and antiphase, and then back to in-phase again when you have a spin echo. And you get complete conversion to antiphase when the delay is 1 over 4j. And remember, that delay appears twice in a spin echo, so the total delay is 1 over 2j. And you also have this rather curious business that when the delay is 1 over 2j, so the total delay is 1 over j, the signal changes sign. So this is a very peculiar system which, when you go around by 360 degrees, changes sign. In fact, you have to go around to 720 degrees to come back on top of yourself. And that's a curious property of these quantum mechanical systems. So that's a spin echo in a homonuclear system. Now I want to have a look at what happens when you do spin echoes in heteronuclear spin systems. And the difference here is that there are lots of variants that you can play. So here's my pulse sequence. Look at A. There's a line for the pulses that we're applying to the I spin, and there's a line for the pulses that we're applying to the S spin. And in A, both of the spins experience pulses. So in fact, it's exactly the same thing as the homonuclear system, so we don't need to worry anymore about that. The offset will be refocused, and the coupling is not refocused. The second option is to only apply the 180-degree pulse to the I spin. Now, what effect will that have? Well, you would expect it to refocus the offset of the I spin because there's a 180-degree pulse, and you would not expect it to refocus the offset of the S spin because you aren't doing anything to the S spins, so it would be unreasonable to expect that they should be refocused. And what I'm going to show you in a moment is that in this version of the spin echo, the coupling is refocused. So that's contrast to the homonuclear case. And the third possibility is to apply the 180-degree pulse only to the S spin. And if you do that, the offset on the S spin is refocused, but not on the I spin. And as I'll show you in a moment, the coupling is refocused in this spin echo. All right, so we're going to have a look at how sequence B and C works and why they're different to the homonuclear case. So we're going to start out with sequence B. The 180-degree pulse is only applied to the I spin, so we expect it to refocus the offset of spin I, and seeing as there's no pulse on spin S, we don't expect the offset of spin S to be affected, and that is indeed the case. And now we're going to do and see what happens to the coupling. So we'll do exactly what we started before. We'll start with IX, but I'm going to use the IS notation because it's heteronuclear. So IX, in-phase magnetization on the I spin, experiences a coupling for a time tau, and that gives me in-phase on X and anti-phase along Y. And then I apply my pi pulse, but remember this time the pi pulse is only applied to one of the spins, in this case the I spin. So that term IX is not affected, because if you pulse X along X, nothing happens. The term IY is not affected. The term SZ is not affected, because that term is not affected by a pulse to the I spin. But the term IY is affected because if you rotate the Y by 180 degrees about X, it changes sign. So this is different to the homonuclear case because the pulse is only affecting the I spin. So then you have to do what we did before, have the second period, and you have to work through all the details. The IX term has to evolve under the coupling, and the IYSZ term has to evolve under the coupling. And if you do all of that, and you put it all together, you'll find that the antiphase terms cancel. Let's go back and look at that. So this term here in 2I1Y ISZ, and this term here, 2IYSZ, they're equal and opposite. So they actually cancel one another. And if you collect together the other terms, you'll see it's cos squared plus sine squared, which we of course know is 1. So the result of all of this is that the magnetization ends up as IX, which is where we started with. So as I said it would be, the coupling is refocused in this spin echo. So if you apply the 180-degree pulse to only one of the spins, it refocuses the coupling, and that's in complete contrast to the homonuclear spin echo. And again, you can go through other operators, IY or 2IXSZ and so on, and see how they're affected by this, and you come to the same conclusion, that the coupling is refocused in contrast to the homonuclear spin echo. And it also works just as well if you start on S spins. So in summary here, in the heteronuclear spin echo, you've actually got a lot of flexibility. Sequence B refocuses the offset on spin I, but not spin S. Sequence C refocuses the offset on spin S, but not the offset on spin I. and both of the sequences refocus the coupling. If, on the other hand, you wanted the coupling to evolve, you could just put a 180-degree pulse on both spins. So that's really why, that's really the origin of the great flexibility with these spin echoes, and we'll see how this plays out when we start looking at multiple pulse sequences, and in particular in two-dimensional NMR. Now, we talked about antiphase terms, and I said they were key, and the reason they're key is that these antiphase terms are the terms that get involved in coherence transfer, as it's called. And you can just illustrate this very simply. Suppose you have an antiphase term 2I1Y I2Z, and then you apply a 90-degree pulse to both spins. So first of all, a 90-degree pulse to spin 1, so that operator then becomes 2I1Z I2Z. And then a 90-degree pulse to spin 2, that operator becomes 2I1Z I2Y. And so what we started out with is an antiphase term on spin 1, and after the pulse it became an antiphase term on spin 2. And that's why that's called coherence transfer, because you've transferred the signal from spin 1 to spin 2. And this only happens because of the antiphase terms. It's only the antiphase terms which get transferred. And if you think about this, of course, the antiphase terms, they only arise because you have coupling. So the presence of coupling leads to antiphase terms, and then these antiphase terms are the terms that can get transferred from one spin to another. And that process underlies all of the important experiments, particularly in two-dimensional NMR. So this is one of the reasons why we focus so much attention on these antiphase terms, because they are the ones that do all the interesting stuff. And that's the end of the second section.